been a whole week.
A whole week.
Thanks to time dilation, says Jason Elric. But still wearing the same clothes last week. Yeah, we've barely changed. See you next time. So I think we exist. We exist part 2. All right. Good.
And I want to say hi to everyone watching out there on Twitch. I think Paranor is currently simulcasting us.
Right on. I've got to get more organized about that. At least like say hi to the people that are over watching us on Twitch.
Yeah.
Because it's becoming a sizable chunk. And you should have changed the view out the window.
I'm just going to keep orbiting this world.
Yeah, I love how that looks. It's so
It's
cool.
it's really cool.
Yeah, like it really has this great. It really does look like the sunshine on some version of the like a window shade that's got little pinprick holes on it. But anyway, yeah, I like it. But really, it's just a green screen, which is apparently a thing. People use green screens. I don't understand it.
So I have a very strange small fantasy involving green screens. I want to set up software so that when we get a new subscriber on Twitch, it looks like there's a window behind me and a supernova goes off whenever there's a new subscriber.
Cool.
So I want to write that data visualization.
I've seen people where like it puts a hat on them every time a new
Yeah,
subscriber.
we have software that does
Okay.
stuff like
Yeah.
that. I just want to do something that's like on brand.
Yeah. Right.
Currently, we just have like rockets that are cartoon rockets that take off.
Uh, Beth. Whoops. Beth, can you
Mm.
say hi in the chat? And while you're doing that, I'm going to say hi to Andrew Planet, Andy Cowley, Astro YYZ, Beatrix Lidner, Bill Sugden, Deepak Singh, Dustin King, Dusty Reichwin, Gordon Dewis, Greg Nickel, Guido Bibra, Janelle Duncan, Jason Elric, John Seffel, Johnny Zed, Kira H, Kylie Cerna, Lindy Sadiq, Michael Bonnet, Michael Meyer, Mrs. Nat, Nancy Graziano, Nicholas B, Niji, Paranor, R. Instro, Rich Wilson, Rich 901, Sergio Botero, Sir Goosey, Side MT, Susie Murph, Therion, Wayne Johnson, Yamagashi-san, and Zapfan. Hey, everybody. There we go. I gotta be really careful. I've added you as a moderator, Beth, but it's really close to put you into a timeout or even cancel you entirely from the
The
it's
buttons.
just the
Yeah.
way the buttons work. Yeah, they line up the buttons so you're just like very carefully like, ban this person forever or make them a
Right.
moderator.
Yeah. Yeah. That and the pictures aren't necessarily intuitive.
Yeah. All right, so if you're wondering what this is, we are now about to do the second episode that we are going to record today. This is going to be episode 549. And then we'll stick around for, I don't know how much time we're going to have after that. We're kind of running over already, so I'm probably not going to have much time to answer your questions. So save them for next time. Or put them on my question show over on my YouTube channel, which I should be releasing a new question show in as soon as I have time. As soon as this is over, I'm going to go and get the question show done and prepped and posted to my channel. So stay tuned. Anything else, or shall we begin?
I think we're okay.
Okay. I'm ready to press record.
I am pressing record. It is recording.
I am also pressing record. Astronomy Cast, episode 549, Stellar Nucleosynthesis Revisited, part 2. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
Good, good. It's been so long. It's been
I know.
half an hour since we talked. So here we are again, recording another episode. Sometimes this just happens.
It's true.
You
It's
hear
true.
it.
We're doing a double today. We're
Yep.
gone next week. We're then doing a double next time. Then we're gone a week.
Right.
Then
That's
we're
when
probably
I'm
doing a, that's when you're gone.
Right.
And then we're probably going to do a double again because
Yep.
of the holidays.
Yes. And then we'll be in the same place at the American
Yes.
Astronomical Society.
Yes.
And so we'll record one of those rare Fraser and Pamela located in the same roughly location of the time-space continuum, which is always fun. Because even though it does sound like we're in the same room hanging out, we rarely are. Mostly we are
true.
time zones apart, recording over the internets.
We have been recording for more years than the number of times that we've seen each other face to face, I think. It's close because we see each other once or twice a year.
Yeah.
But then we've occasionally gone years without seeing each other early on because we didn't have as much. We were younger and stupider.
Events to go to. Yeah.
Right. So, yeah.
Last week, we gave you an update on the formation of elements from the Big Bang and in main sequence stars like the Sun. This week, we wrap up with another bang, talking about the death of the most massive stars and how they seed the universe with the heavier elements. And this is the part where hopefully that we're going to get to with all of the new news, all of the new research that has changed dramatically since I have been informed the last time we tackled this was episode 109. Nucleosynthesis.
It's true.
So it has been a good 400 plus episodes since we talked about nucleosynthesis, and there have been some dramatic events that have really helped us understand where the stuff came from.
So I think a good place to start is let's review where do things come from that we've discussed so far. So we have hydrogen, helium, largely from Big Bang fusion, a little bit of lithium and beryllium in there as well. Then we have low mass stars when they puff off their outer atmosphere. Here we're getting carbon and nitrogen. We also have some other things that happen in the outer atmosphere of stars where we end up with things like lithium and strontium and annoyingly technetium and lead and cadmium. So there's a lot of elements that are shockingly built in the atmospheres of stars and then just get puffed out in planetary nebula. Now, where things start to go sideways is when either bigger stars go boom or little stars suck material cannibalistically off of their neighbors, become big stars, and go boom.
Right. Which version? Let's start with the first one.
Okay. So giant stars. Here I'm talking things that are significantly larger than our sun. When they die, they have so much material left behind that instead of collapsing down to form a white dwarf, they collapse down and try to form a neutron star, and in the process can expel matter, or they collapse down and try and form a black hole and expel matter, or they just explode and leave nothing left behind. And the reason I simply say significantly larger than our sun is because we don't fully understand mass loss rates in the largest stars. And so it's reasonable to expect that it may be objects that are 10 solar masses or higher at their beginning that are still big enough to produce these explosions when they end their lives. it's all a matter of electron degeneracy pressure giving up the ghost. Stars are supported with light pressure pushing out and gravity pushing down. And when you don't have enough light pressure pushing out, the atoms attempt to get as compacted as they can. And at certain phases in giant star evolution, you can end up with a degenerate core that will undergo a helium flash. And in the death of smaller stars, as it collapses down, the electrons all compress tightly together and go Pauli exclusion principle and make sure that things align with the correct spins and energy levels, that it actually is able to support the star from collapse. But electron degeneracy pressure can only support so much mass before it's overcome. And when that occurs, the atoms go, electron and proton can save space by becoming a neutron and giving off a blast of energy and particles. And it's that blast of energy and particles that is one of the ways that we end up with supernova occurring.
And I mean, I always also sort of imagine it like in the cores of a star like the sun, as you mentioned, like you've got the hydrogen getting turned into helium. When that runs out, you can turn the helium into carbon, you can turn the carbon into silicon, but eventually the star just runs out of enough pressure and temperature to keep that process going, and that's when you get that thing to cool down. But with the
And
more
and
massive stars, they just keep going. They just,
and and you end up with an end to nuclear fusion in two different routes. There's the one that you just hit on of it's not hot enough to go any further. So our sun is never going to be burning silicon in its core. It's never going to be building neon in its core. More massive stars can do that. And for them, it's not a matter of, oh, we're no longer hot enough and dense enough to have nuclear reactions. It's a matter of we're out of fuel and there's no atoms left on the periodic table that give off energy when you use fusion processes to produce them. So you run
right,
out of the ability to generate that outward
right,
flow of photons, that outward pressure that sustains the star.
right. So
No
the
outward
the
pressure,
the
death.
the fusion reaction is exothermic. The fusion reaction gives off heat with hydrogen, with helium, with nitrogen, with carbon, with silicon, with neon,
Right.
all the way up. But the really heavy elements, the uranium and and technetium and things like that, they require energy to be able to be fused together. And the
Well,
and the point of balance, the 0 point, is when you get to iron.
and even cobalt on nickel that are just a couple elements higher than that iron. Here you're requiring something to explode in order to not worry about the loss of energy that's necessary to create that especially dense core. You build iron, and up until that point, you release energy. As soon as you get to cobalt, it takes energy.
Right. And so then up until this point, you had all this energy being blasted out that was holding the star, that was keeping the star inflated. And then when you get to iron, you no longer have energy pumping out of the core of the star, and you get the collapse.
Exactly. And during this collapse, the gravitational potential energy of all of this supported atmosphere gets transferred into kinetic energy. You have the entire system getting smaller, you have energy going into the system. And with all that extra energy available, and the system's heating up and the pressures are going up, you're now going to be driving nuclear reactions of a different type. Some of that gravitational potential energy, it's completely happy to join forces and, well, be, be what drives the generation of these heavier elements. And so, with these exploding massive stars, you're starting to get things like arsenic, krypton, rubidium. These are cool atoms that, well, we have only because of the explosion of massive stars.
And what are, you gave a bit of a sneak preview, this idea of this, that there was a fast, what did you call it? The fast
It's
neutron,
the rapid process.
the
So we
rapid
have
process.
so
And that's
so
what's
the
going on here.
that's some of what's going on here.
Okay.
So the rapid process is where you have some fusion going on that's generating massive amounts of neutrons. Those neutrons are flying out at a huge rate, and as they do, they are bombarding the atomic nuclei of other atoms, building them up with neutron, 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 and then you can get cascading events that take you down to stable isotopes. So essentially, you build up something entirely unstable, and then those neutrons begin cascading down, becoming protons, changing the um, nature of the atom while conserving the number of particles in its center and allowing bigger elements to come into existence.
And you said that this was part of the process.
Right. So we have that going on. We also have release of all of the stuff that was already built in the center. So there's two different things going on. You have to release the stuff that already existed and you have to create new stuff. So aluminum, all of the aluminum that we deal with, it was released through the explosion of a star. And it's not one of these super heavy elements that we talk about in terms of being formed in the supernova event.
So the
It's simply
aluminum might have already been built up before it hit the supernova stage.
exactly.
Right. But then it was the fact that the star detonated itself, which was how the aluminum got out into the universe, because otherwise it would have just been trapped inside of it.
Right. So here we're looking at things like oxygen, aluminum, arsenic. All of these things are coming from these exploding stars. Now, again, we also have the proton process that builds things up. That's a much smaller event. But at the end of the day, fusion, which can occur with energy getting absorbed out of the gravitational potential energy, can drive some of the reactions. Neutron processes drive some of the reactions. And then you're just freeing the stuff that was already there.
Now, you mentioned that there's sort of a few different ways that these straight core collapse supernova can happen. In some cases, they just blow themselves completely apart. And in other cases, they do form some degenerate object, a neutron star or a black hole. And so some of that material has got to go into it all gets turned into neutron star, or it all gets turned into black hole.
Exactly.
But some of
And
it gets out.
so it's a ricochet process in some ways. You have all the outer layers of the star collapsing down, and the inner layers are also collapsing down. You have to remember that part as well. It's all getting crushed down. And the innermost part will ignite or become the neutrons giving off energy as the protons and electrons combine to form those neutrons. And so you have stuff falling in at the same time that you have this shock wave radiating out. And that will trigger nuclear reactions in the outer parts. Now, how much energy is given off is a function of what was the progenitor star. Is this something that's forming a neutron star? Is this something that's forming a black hole? And also, at a certain level, what was the prior composition of the star? Because depending on what you have seeding its atmosphere, you're going to get different outcomes. But that's a secondary effect that we don't worry about as much.
And
Mostly,
even
we look at these two mass regimes.
right, and even just like what you get, there's a ton of different factors, and there's still astronomers are still trying to figure this out, because in some cases they just turn into a black hole and wink out of existence. So, and in other cases they do get a nice bounce and all this material comes flying out. In other cases the thing just tears itself apart completely and there is no black hole. So these are the nuances that astronomers are still trying to figure out, and they have amazing simulations where they will use up years worth of computing power one death of one star to try and figure out what's going on inside them at those in those last moments of their lives.
And what's really cool is just looking at how different models are trying to figure out, as the star undergoes the supernova, you see this increasing in brightness over a fairly significant period of time that isn't measured in minutes. And this longer period of time that gets you over days to the peak brightness that then recedes over weeks, um, that is attributed to the energy transport mechanisms, the ongoing reactions that end up taking place with the shock waves. This is an evolving process. It's not a instantaneous thing as we'd like to imagine in our
Right.
head or when watching Star Trek.
Right. Yeah. Captain's log, where the star is about to go supernova and we're going to watch.
Right, exactly.
Yeah.
It's sure, but you're going to be there for a little while.
Right. Now, you talked about this other way where one star can feed off another star, and this is the Type 1a supernova. What
So
different mechanisms are what different mechanisms are forming elements in a star like that as opposed to the core collapse?
So what's cool is you actually get two different kinds of nucleosynthesis associated with white dwarf stars. And one of these actually exists also in neutron binary systems. So when you have an accretion disk around a star, and when you have a white dwarf star, you can have the material that's getting cannibalized off of a nearby neighbor build up and build up and build up until it undergoes its own nuclear reactions. When we look at quasars, the accretion disks that are giving off as much light as an entire galaxy, that's driven by nuclear processes. So we can have accretion disk nucleosynthesis going on. This is a completely different place that we usually ignore because it's not a dominant player, but it's a source of light. It's a source of nova. It's the source of what makes active galactic nuclei. And
And so
this
if you were
is
to look at one of those accretion disks and actually peek inside and see the fusion that's going on in there, what would it be analogous to? Would it be like a main sequence star? Would it be like a supermassive star? Would it be like colliding neutron
here we're
stars?
here we're probably looking at proton proton chain events where we have these bursts that are the nova that we see so often. You can also end up with white dwarf with infalling material building up on the surface of the star until it ignites.
Right.
And so these different mechanisms where you have recurring nova, cataclysmic variables, there's a myriad of different names for these violent binary systems where material pulled off of a neighbor onto or into the vicinity of a compact star, that pulled off material gets gravitationally crushed, builds up to such a high pressure and temperature that it ignites. In the case of cataclysmic variables, recurring novae, these are temporary events. In the case of accretion disks, these are prolonged reactions, which, as long as that system is a quasar or an active galaxy, you have nuclear reactions going on in that accretion disk.
So in 2017, astronomers saw evidence both from gravitational waves and from the visible explosion of two neutron stars colliding with each other. And this had been thought to be one of the ways that the heavier elements come into the universe, but it was still only theorized. But in the wreckage of that collision, astronomers did see the heavier elements. They saw gold forming. They saw heavier elements that we had thought might only have been able to come from supernova. So how did that sort of change our understanding, and where does that fall in this classification of different kinds of nuclear synthesis?
This this is one of those things that is such a new result that I have to admit I haven't even been able to find an updated uh, periodic table that shows the origin of elements that includes which elements are all derived from um, white dwarf uh,
Neutron star
combination
collisions,
mergers.
yeah.
Yeah, sorry, neutron star collisions. Um, with neutron star collisions, what you're dealing with is you have two different systems that have each undergone the we're going to release all of our energy. But neutron stars are thought to have normal matter on their surface.
Right. They're not 100% neutron stars. They've got a sort of a crusty exterior of other stuff.
And so it's not like they're solid marbles of neutron star that you can just sort of touch to each other and they're happy. They also have magnificent magnetic fields that, when these field lines recombine, give off gamma ray bursts of energy capable of destroying satellites from across the galaxy. These are powerful systems that have a lot of different things holding energy inside. Now, when you take two of these systems that have massive magnetic fields, that have regular non degenerate matter on their surface, and you bring them together, you have the rearranging in the magnetic fields, you have the ignition of the non degenerate matter that heats everything up, removing the degeneracy of some of the matter, but then, oh, expletive, the total amount of matter is incapable of having sustained nuclear reactions, and it's forming a new, bigger object. And depending on what's left behind, it could be a black hole, it could be another neutron star, depending on where you are on the size of the neutron stars. And all of this is going to release new energy in new ways and produce gold.
So,
This is where you get gold.
and so, like, specifically, like, I'm just imagining. So you've got a neutron star, you have it surrounded in other material,
Yeah.
they collide. Where does the gold come from?
Well,
Is it
so
from the neutrons being smushed together and them decaying into gold like we talked earlier, or is it from the elements that are surrounding the neutron stars that are then being merged into these heavier elements? Like,
you oh man.
did we stumble off your knowledge space?
Yeah, you stumbled my knowledge space. I don't know the detailed answer to that. I'm
Okay.
just going to have to say I don't know
You
the
can just
detailed
ignore
answer to
that
that.
question that I asked.
Okay,
Yeah.
Susie, make that
Yeah.
go away.
Um,
Sorry, Susie.
One of the things that I find really fascinating, and I don't know if you followed this story, was based on what happened with the kilonova. Astronomers then went back and did some calculations about where a lot of the heavier elements from here on Earth came from, and predicted about where and when a neutron star collision in our environment must have happened to help seed the solar system with the heavier elements. So it's a
And this all comes down to looking at what are the ratios of elements that come out of these different processes. So if we know that aluminum comes from exploding massive stars, that tells us that we have a lot of aluminum, therefore there had to be a nearby exploding massive star. Now, gold comes from a variety of different places, but each of these different places produces it in different ratios with other atoms. So if you know this thing over here produces a bunch of these things, if you know this thing over here produces a bunch of these things, and you know the resulting set of ratios you need to get because you can go grab rocks in our solar system and sample, you can actually start to say, okay, a solar system like ours needed 3 of this, 2 of that, and that gets us to the ratios of what we see. We're not a first generation, we're not a second generation, multiple generations of multiple kinds of
yeah.
dying stars in different configurations had to go into what we see in our particular solar system.
And so it's kind of amazing, right? We bring it all home and we think about where my chair and my house and the air that I breathe and the water that I drink and the gold in my electronics, where it all came from. It is all of the above. It is from the atoms that were formed in the first moments of the universe. It's from the heavier elements that were produced in the core, that were generated in the atmospheres of other stars, in the deaths of the biggest stars, in the collisions of dead stars, and all of that, like a soup, like a gumbo, came together to make all these elements that we depend on
You're
for
making
everything.
it sound so prosaic. And of course we've all heard the phrase we're all made of
Made stars,
stardust.
yeah,
But we need to recognize we're not just made of star stuff. We are made of the shredded, regurgitated, exploded out
yeah,
remains of stars
super
that had to be
concentrated.
torn up
Yeah,
and scattered to all
yeah,
directions.
yeah. And then though that material was eaten by other stars and then vomited out and blown off into space. Yeah, no, it's not a beautiful, majestic process. It's just death over and over and over again in many different ways. And here we are.
And here we are. And it's kind of awesome. And it's kind of awesome that it hasn't been a straight line to figure it out. There's been a lot of times that we thought we had it figured out, even until recently. And we weren't entirely there. And I'm sure there's still stuff we're missing. But to just realize that when we look out across space and we see things lit up in the night, we know that that is either an ongoing nuclear reaction or the residual heat of a nuclear reaction. And that means stuff is getting made. Supernova remnants are the remains of an exploded star that are shining in the night. Quasars are ongoing reactions where there's no star. It's a disk of material getting torn apart by a black hole that is lighting up brighter than all those stars. And I don't know why we don't point that out.
Mm-hmm. Yeah.
A quasar is brighter than the stars because of nuclear reactions not taking place in stars.
Right.
And that's awesome.
Yeah. Yeah. Well, I think on that note, then, I tried to make it more poetic. You made it just a horrible nightmare.
The universe is trying to
I
kill
know
us.
it really is. And it's just amazing that we're here at all. So, Pamela, thank you so much. We'll see you next week. But before we do you have some more names for us?
I do. And it's a long list because apparently at some point this month, I didn't read enough names. So for November, our final round of patrons are Dean, Ryan James, Kristen Brooks, Kensla Penflenko, Darcy Daniels, Shannon Humber, Rachel Fry, Gregory Joyner, Dwayne Isaac, David Gates, Eric Farringer, Jessica Feltz, Justin Proctor, Thomas Tubman, Claudia Mastriani, Tyrone Fong, Robert Cordova, Frederick Shorg, Neuter Dude, Arthur Latz Hall, William Andrews, Kevin Nitka, Jack, Jeremy Kerwin, Brandon Wolverton, Joshua Pearson, Brent Nearnop, William Lauer, Mark Stephen Raznak, Brian Kelby, Tim Garish, Joe Wilkinson, Omar Del Riviero, J. Alexander, Dustin A. Ruff, Chad Colopy, Dean McDaniel, Nala, and Aaron Segev. Iran Segev. I know you. I don't know why I mispronounced your name.
Thank you, everyone. And we'll see you all next week.
Thank you.
Save.
Yep.
And then I think, unfortunately, everybody, we've got to now wrap up and move on. So no time for questions this week.
I'm sorry.
But you could chase Pamela on Daily Space, right?
Yes. So the one question I will answer is, how long after the Big Bang was there enough CNO, et cetera, to begin life? And the answer is, we don't know, but it could have been as little as a few 100 million years after the Big Bang, when we know that multiple generations of star formation had taken place.
Right. Awesome.
Okay.
Okay. Thanks, everybody. What's happening? Next open space on Monday. So you should come join me. It's at a funny time. It's going to be at 9 o'clock. So stay tuned for that. All right. We'll see you all next week.
Okay. Bye-bye, everyone.
Except we won't. We won't see them next week. We'll see them in a couple of weeks. All right. Now I'm pressing the end. Have a good Thanksgiving.
I will. Enjoy your week.